Hey, what's up, guys? So let me just give another application of cyclotomic field, cyclotomic polynomial. So in this video, let's prove every finite abelian group is the Galois group of finite extension of Q. Okay, so this is the inverse problem. Okay, so the inverse problem, this is still open. So the task is that given a finite group, so it's given a finite group G, and the rational field Q. So the goal is to whether there's a L finite extension over Q such that or the Galois extension. So let's assume it's Galois, such that the Galois group L over Q is isomorphic to G. Okay, so this problem is still open. But this using a cyclotomic field, then one can prove that for any finite abelian group that this is true. So the results basically we will prove today is that when G is abelian, then the answer is yes. Okay, so let's recall, right? So there's a fact that I think it's easy that you can prove by yourself, is that if you include the unprimitive roots of root of unity and ask the Galois field over it, then it will become the Zn cross. So Zn cross basically is the element M, which coprime with n. Okay, this is simple that you can prove it, but because the root of unity and primitive roots will just permute the Galois group in it will just permute roots. Then when you permute roots, is the same as you must permute the roots. Because these roots, right, involve all this number which GCD up to n. GCD is up to 1. Okay. Okay, so we can solve this inverse problem by a very simple technique. So let's solve the case 1. So case 1 is just a simple case. So let's consider let's consider our group to be cyclic, right? So it's C A and the G is order n. It's maybe a good bad notation. Yeah, it's fine. It's n. And so we can consider define a P, right? We can find a P which is 1 minus n, because for a cyclotomic field that we have infinite, right? We have infinite P such that this is true. Okay, so if we add the Galois group of Q omega P over Q, will isomorphic to ZP cross, which is cyclic. So this guy has order P minus 1. Okay, but P is 1 minus n, so that means that n divides P minus 1. Okay, so what? Okay, so let's yeah, so yeah, n equals to, okay, so n divides P minus 1. Okay, so that means that there's a subgroup H inside ZP cross such that the ZP cross quotient H is exactly n. Right? It's exactly cyclic because ZP cross is cyclic, and so H is a subgroup is a cyclic. So this guy is a normal extension, right? So you can, or normal subgroup. So this will isomorphic to A. So basically from this that you already proved this. Okay, then by Galois theory. That any subgroup of either Galois group corresponding to the finite extension. So there's a LH. Okay, let's say this is L, and then LH is a L, the subfield of L are fixed by H, and it's what we want. Because the Galois group of LH will be the group of A. Okay, just this. Okay, so now we can consider the general case. So for a general case that we can consider G to be finite abelian, right? So finite abelian group can be direct sum cyclic. So we can write Cn1 direct sum Cn2 direct sum Cn3 up to CNR. And each Ni is cyclic. And with order, that's with order like Ni. Okay, so now we can find a distinct, Pi such as 1 mod N1 up to NR. So there are, so I from 1 to 2 to N, and there are infinite of prime. So we find a distinct R of them. So distinct R of them. Okay, so now we can, we want to construct a field, right? So we can consider the Q. We can consider N to be N1 up to NR. And then we consider our large field Q is Q at joint omega N. So the Galois group of Q over L over Q will be the cyclic group Z of N cross, right? And the Z of N, since they are each are coprimary to each other. Sorry, this is P1 up to PR. Okay, so since P1 up to PR are coprimary, so you can it's isomorphic to Z P1 cross direct sum Z P2 cross up to Z PR cross. And we know that from this that we know that each N, for example, the P1 minus 1, N1 divides P1 minus 1, and N2 divided by P2 minus 1. Okay, so that means that you can find a subgroup H1, H2, and up to HR. Okay, so that means that there is a subgroup H1, direct sum H2, up to HR, such that the Galois group of Q F's omega N over Q quotient H1 direct sum H2 up to HR is what? It's isomorphic to Cn1, Cn2, Cn3 up to Cnr, right? Because I can N1 divided by Pi minus 1, so there's a indexes. There's a subgroup which indexes N is N1. Okay, so we finish the proof. Okay, then we still use the Galois theory. Okay, so this is the one example that you use their infinite prime, which is 1 mod N, to prove that every finite abelian group is the Galois group of finite extension of Q. Okay, see you guys next videos.